The first move to actually making what we would class as 3D PIV, or volumetric PIV, is actually an adaptation of stereo PIV. In fact, what you have here is two stereo PIV systems operating simultaneously and observing two parallel light sheets, or overlapping light sheets in some cases. So we're taking two almost simultaneous stereo PIV measurements. So we have three components of velocity measured over a two-dimensional plane, and then again over another two-dimensional plane with a fixed separation between. You imagine setting a system up like that can be a little bit, it's component intensive. You need basically two PIV systems. The primary interest in setting such a system up is actually to measure the vorticity in all three directions. If you have the velocity sampled in two parallel planes, you have the possibility of calculating the spatial derivative of the velocity field in all three directions. Again, so it resolves the complete velocity gradient tensor, albeit over a planar section. It's not through a well-developed volume. It utilizes conventional stereo PIV technique, and that can be put together with stuff that's well known. It is limited to planar section, and it's very time-consuming to adjust the sheet positions and set the overlap. I spent quite a bit of time at the University of Michigan in 2001 working with John Mullen, working on the system. In his system, he had two different colors of light sheet and used filters on the cameras to separate one plane from the other. But in this paper by Kahler and Kompenhans in 2000, they used polarization. So the laser sheet for one system was orthogonally polarized relative to the other. Moving a little bit further ahead, there is, in terms of the volume that can be accessed, there was some very interesting work done in the 90s by Christoph Brucker, and I think he still pursues this technique of basically scanning a laser sheet through a volume. So you have a laser sheet illuminating one planar section, and a high-speed camera records that PIV measurement on that plane, and then it translates to a parallel plane by using this oscillating mirror, or separately controlled mirror, which allows the sheet to be scanned from one plane to the next. The idea is that the video camera has a high enough frame rate, and the sheet is scanned at sufficient frequency, high speed through the volume, that in the time that it takes for the sheet to progress from the back to the front, or from the front to the back, this constitutes one measurement, and this time from front to back should be short compared to the time scales of the flow. It can be used with a single camera or done with a pair of cameras using stereo PIV. If you're only using a single camera, you can actually use continuity. It can be used to resolve the out-of-plane component in some special cases. It can only be classed as quasi-simultaneous. It does take a finite time to translate from the front to the back. And because of this, it's limited to slowly evolving flows. And it requires a high frame rate camera to resolve the depth, and presumably a high ref rate laser if you're using a pulse laser or a fairly powerful CW. Volumetric techniques, the whole field of photogrammetry is the use of multiple cameras for viewing an object or a field of view from multiple perspectives to resolve three-dimensional shape or three-dimensional motion. And that can be used in a PTV or particle tracking type application, as it is here. Particle tracking velocimetry in three-dimensional flows. This is basically looking at a volume illumination in a tank using three cameras to view a volume inside this region. Each camera has its relationship to the real world volume mapped out using a calibration target, just in the same way we do with atomic PIV. And basically you're identifying particles in 2D, so from each frame you're identifying individual particle locations, measuring that location to subpixel accuracy, and storing the result. And doing the same operation from each camera perspective. Here's two perspectives are shown, but actually in the application 3. And the reason for using 3 or 4 cameras, either photogrammetry or tomographic PIV, will be shown later. But the idea is that you identify the locations in 2D, and then by virtue of your calibrated camera perspectives, you can resolve 3D locations and then track that 3D coordinate from frame to frame. And doing so, you work out the trajectory and calculate the velocity. The key thing here is if you're doing particle tracking, the particle matching, if the particle matching is going to be performed reliably, you're limited to a relatively low number, several thousand particles. You have to be able to identify the connections between or match the particles without getting confused with neighboring particles. And so the seeding base is to be lower.